Our trigger at week 2 was to design an earth berm to protect Thomond Village from flooding, or to design a detention pond berm to provide the UL campus with a sustainable greywater supply. Our group chose the first option. From precedent studies, we know that the Thomond Student Village flooded in the year 2009. One of the first things was to conduct a site investigation, which consisted of 2 phases. Phase 1, which is the information gathering from available records such as maps and published documents, from studying aerial photographs, from site inspection, from company records, and from interviews and contacts.
Wear a safety hat. The consequence might be walking into the digger, or soil might fall as it's being lifted. Wear a high visibility jacket for visibility to avoid contact with digger. Stand far away from trial pit. Never ever ever enter a trial pit unless the walls are reinforced due to possible collapse. Stay away from any machinery. Give plenty of clearance. Contaminants might affect skin, therefore leading to skin irritation. This is prevented by wearing suitable gloves. A trial pit is an excavation of ground in order to study or sample the composition and structure of the subsurface, usually dug during a site investigation, a soil survey or a geological survey. Trial pits are dug before the construction. They are dug to determine the geology and the water table of that site. Trial pits are usually between 1 and 4 meters deep and are dug either by hand or using a mechanical digger. Building and construction regulations clearly state that any trial pits that concede deeper than 1.2 meters should be secured against structural collapse if they are to be entered by people. We then will notice a crack occurring at the right hand side before the trial pit begins to collapse.
Once we had collected samples of soil from our trial pits, we brought them to the soils lab. We carried out experiments on the soil to determine the properties and characteristics of it. The 2 main types of soil that were present in the trial pit were tested, a sandy soil and a clay. The following experiments were carried out: shear vein test, moisture content, sieve analysis, Atterberg limits, Proctor test, California bearing ratio, moisture condition value, falling head permeability test. The shear vein test was carried out on site to measure the shear strength of the soil. It is an indication of sensitivity. Both undisturbed and disturbed vertical shear strengths were measured and a value of 2 was calculated, indicating that the soil is sensitive. The moisture content of the sandy soil was determined to be between 36 and 38%, and that of the clay was between 40 and 43%. Our sieve analysis results were inconclusive, as we ran into a number of difficulties when carrying out these experiments. We did, however, make an engineering judgment that the type of soil that was used for the following experiments was clay. The Atterberg limits are a basic measure of the nature of a fine-grained soil. Depending on the water content of the soil, it may appear in 4 states: solid, semi-solid, plastic, and liquid. Above the liquid limit, the soil flows like a liquid, and below the plastic limit, the soil is brittle and crumbly. The plastic index can then be calculated from these limits. This is the size of the range of water contents where the soil exhibits plastic properties. The purpose of the Proctor test was to determine at what moisture content the maximum dry density can be achieved for maximum compaction. The zero air voids line was drawn to ensure that our results lay below this line. A dry density of 95% will be specified for the berm to allow for a broader range of moisture contents. The California bearing ratio was performed to calculate the bearing capacity of the soil. This is important to determine whether or not the soil can support the plant that will drive on it during construction and the weight of the soil from the berm above it. The moisture condition value is the compactive effort or number of blows required to compact a soil to its maximum density using a specific weight rammer. The falling head permeability test measures the time it takes water to pass through a specified volume of soil, while the falling head is measured at different heights. From this, the permeability coefficient K can be calculated. This is the basis of our flow net calculations.
Berm design. When looking at the design of a berm, there are many different variations in the design and specification, depending on its purpose. In our initial design, we had looked at a landscape type design, which we were quick to realize would not work for the purpose we intended. This was because these types of earth berms or mounds, nicknamed town and garden dams, are relatively low and consist of a well-draining granular core to allow for the drainage of water. This is the complete opposite to what we are trying to achieve. The purpose of our berm is to control the movement of water and protect Thomond Village from rising water levels and potential flooding. Therefore, you could say we are trying to resist and control the infiltration of water. This led us to our next design. This type of berm is controlled by a well-compacted, high-density clay core and steeper slopes. The core is surrounded by a semi-permeable sandy clay which allows for the limited passage of water through the berm. In a well-constructed berm, this soil will resist slumping when wet. We also included a downstream rock toe to handle the seepage in the berm, which could potentially weaken the structure. Its principal function is to provide drainage and also to protect the downstream slope of the berm against tailwater erosion. After giving our design more thought and considering our options, we came to the conclusion that this type of design was far more complex than required for our purpose. In large-scale projects, the supply of available clay is limited. Therefore, it is practical to use a clay core. Because our proposed dam is on a smaller scale, it is okay for us to use all clay in the design. This type of design is called the homogeneous dam, and this is what we use for our final design. It is made entirely of a single impervious material, high-density clay, with no core. In addition to this, we introduced a small section of rock toe, a pervious material on the bottom of the downstream slope to control seepage, as well as a sand and gravel filter. To construct our dam, the upper layer of coarse-grained soil shall be removed, and the berm shall be constructed on top of the existing clay. It is then constructed by rolling or otherwise compacting layers of the selected soil in succession. Initially, the compaction process squeezes out the air, but as the height builds up, the lower layers experience an increase in pore pressure, which slowly dissipates over time. Now let's look at seepage. The solution of a practical seepage problem is represented by flow lines and equipotential lines, which make up a flow net. This is done by letting a flow line equal a streamline. The fundamental conditions to be satisfied in a flow net are that every intersection between flow lines and equipotential lines must be at right angles to each other. Therefore, the flow lines and equipotential lines form curvilinear squares throughout the flow net. It is important to remember that flow in soils is slow and assumed to be laminar. Post-construction health and safety plan. Construct a fence around the berm to prevent people from climbing onto it. Place signs around the berm to warn people of possible hazards. Routine maintenance must be carried out to ensure that signs of potential failures may be recognised in time to prevent them.
Life-saving equipment must be available at regular locations along the length of the berm for use in the case of an emergency.